Hello everyone. After the hands-on session, now I'm going to summarize parallel programming concepts and some important features of alpaka. Initially, I would like to talk about grid hierarchy. In parallel programming, kernels are executed on a grid of multiple threads that run on a GPU. Threads are the pieces of a process that do the work. Each dimension of the grid is partitioned into equal-sized block of threads, and each thread has an index. Threads are actually things that do the work, and they have as a block they use a common shared memory, and each thread uses per thread local memory. And knowing GPU structure is also useful in parallel programming. GPUs have different memories with different size, latency, and bandwidth. Global memory, shared memory, constant memory. For example, threads are matched to GPU cores. That is important, and a block of threads matched to the cores of a compute unit or CPU in parallel programs. GPU global memory is slower, but all threads of the grid can access to the global memory, which is here, the global memory. Shared memory is a block level memory and a fast memory. All threads in the block can access to it. And we will have a session using global memory first. Then later on, at another hands-on, we will use an example using shared memory. Knowing this memory hierarchy is important sometimes in understanding bottlenecks or upper bounds of the code we are running, and upper bounds of the performance we are running. I would like to talk about some thread parallel programming terminology. Alpaka uses a grid block thread-based parallelization model. The model is instantiated differently on different processors because of cache size and cache speed, the synchronization mechanism, or simply the difference between CPUs and GPUs. By using this abstraction, the execution can be optimally adapted to the available hardware. This is actually the reason behind this grid block based model. Secondly, the assumption is that large number of threads should run the same code on different data in a parallel manner. And lastly, indexing of threads is of course needed. Each thread should work on a different data portion or do a specific task. Therefore, each thread has an index accessible in the kernel. And indexing of threads, you can see that from the first grid on the right-hand side. The grid block extent. Extent means the size actually. And the grid block extent in the first image on the right is 3 because there are actually 3 blocks. And block thread extent is a single item vector or array, and the item is 4. And in the second one, you can see that it is a 2D grid, and grid block extent is 1, 3 because there are 3 blocks and 1 row of blocks, and block thread extent is 4 and 5, an array of 2 items, which is 4 and 5, And because each thread block, the size of the thread block is 4 to 5, and the order is important. And grid block extent is 1 3, not 3 1, or block thread extent is 4 5, not 5 4. Yeah, the order of extent is important. I would like to talk about a vector on a specific problem. Yeah, this is a vector addition problem. Let's assume that we want to sum two vectors by utilizing parallelism of the hardware. We have two one-dimensional vectors, vector A and vector B, and we will calculate the sum of two vectors. In order to calculate the summation, we need to distribute the data to the threads. That means we need to map threads to each data item. In this solution, one-to-one mapping is used. Actually, an identity function between thread indices and the data indices is used. Thread 0, for example, will add A0 and B0 to find C0. Thread 1 will add A1 plus B1 to find C1. But as we have seen, we have a grid block structure in parallel programming. And it is called work division in alpaka. For example, we can create a grid block structure using a work division which has n blocks, and each block has 4 threads, and we have a thread element extent. Currently we can take it 1. Yeah, I will explain it later. What is work division here? Let me explain in the detail. In alpaka work division has 3 vectors. Each vector shows the extents or the size of each level. What are the number of blocks along each dimension? The work division representing the upper grid has 3 vectors. Each has 1 element, and the first vector is a single item array M. The other one is 4. The other one is 1. Therefore, 1D work division has 3 vectors, and 2D work division has 3 vectors. M by M block. M by M is the grid. 2 by 2 is the size of the block, each block, and 1 by 1 is the thread element extent. We usually take it 1 now. Blocked. Okay. Yeah. Here I would like to talk about difference between sequential and parallel vector sums. For example, on the left you can see a sequential code. There is a for loop, and for loop in the for loop an index is generated, and the 2 arrays are summed to find elements of C. And on the right hand side you can see the alpaka kernel, and in the alpaka kernel there is no for loop. And how the index is generated in this kernel? Index is magically actually generated, and we can access to the index directly. Then we are using that index, and each thread is going to call this kernel, and each thread will have of course a different thread index. then this summation will be done by a grid of threads to find the resulting array. But we need to also know the bounds of the for loop. Here bound is n. It is obvious, but this is in this kernel we don't have any bounds. It is just like inside of for loop, and we define those bounds in the work division given before, and work division is given while executing this while executing this kernel we defined above. And this is an OpenMP code which can be used for CPU parallelization. And as you can see, there's a pragma line to make the for loop parallel. By this pragma line, this code converted to a parallel code. Actually, it is not difficult for using on CPUs. Alpaka is also using OpenMP as a backend. What is alpaka kernel? Alpaka kernel is actually a function object or lambda. Kernel consists code that is run by each thread. Alpaka kernels are functors, namely structs with specifically implemented function operators, or it can be lambda. Here we have a function object, not a lambda. And before calling a kernel, we need to select the backend. Then after selecting the backend, we can execute the kernel. In the second code piece, a lambda function is used as a kernel, and we can get the indexes of the thread or extents of the grid, then print them. This is what this kernel is doing. Arguments to the kernel should be built-in types or pointers. For example, here we have an integer, and as you can see, each kernel takes ACC as an argument, which is the accelerator instance. Yeah, that's all I can say.
So there is a question online which is asking, what is the meaning of alpaka function ACC?
Sorry, which one? Which function?
Alpaka FN ACC. What does it mean?
Ah, okay. Let me explain it. Yeah. Yeah, we have alpaka function qualifiers, and if for functions called directly from accelerator code, we use alpaka FNACC function qualifier. If it's going to be a function which is callable from host or ACC, then we can use an alpaka function qualifier, which is alpaka function host underscore ACC. And if we use a function qualifier, which is alpaka function host, then it means the code will only run on the host side. Yeah, if no qualifier is used, it is the same as using alpaka function host. These are the function qualifiers and used by alpaka to differentiate between ACC and host code. Someone who is familiar with CUDA would easily understand the meanings of these qualifiers, I think. Yes. Now I would like to go over getting the index in the kernel. Obtaining the indices of threads or blocks is easy in alpaka kernel thanks to using of function templates. Using getIDX function with different predetermined alpaka specific templates would be enough to get the thread index in grid or in block, or the index of block in the grid. For example, the index of the selected thread is 7 in the grid. As you can see, it is the 7th thread in the grid. It is the, therefore, the getIDX, if getIDX is used with grid and thread types, then it is going to give us the index of thread with respect to the center of grid, or with respect to grid, we can say. It is the 7th thread, and it is the third, or it's the fourth, or the thread with the third index, the thread with index 3 in the block. Therefore, thread block index is 3. You can see block and thread types are used here. And getting the block index in the grid, we should use grid and block types, and this is the second block which has index 1, therefore block grid index is 1. Obtaining in extents in the kernel is also easy. We are just using a kind of a function which is named getWorkDiv. If grid and thread types are used, then it means we are going to get extents of the grid, and the unit will be threads. And grid thread extents will be a single item array, and the array will have 4m, an item which is equal to 4m. And block thread extent is also 4, because block has a size of 4, and and we have m block, therefore grid block extent is m. We can also give an example using a 2D grid. Grid thread index of the thread selected is 1 and 9, because it is in the first, in the second row with an index 1, and it is the 9th, it's the 10th thread in the row, which it has an index 9, therefore grid thread index is 1, 9. Thread block index is 1, 4. It is clear with respect to block, it has an index 1, 4, and block grid index is actually 1. It is the first block. It's the second block with index 1. To extent of these blocks and the grid can also be accessed by using getWorkDiv function. For example, grid thread extent here is 415, because there are 4 rows and 15 columns. Therefore, grid thread, the size of the grid is 4 by 15. The size of the block is 4 by 5, and grid block extent is 1 by 3, because there is 1 row and 3 blocks. And coming back to the vector addition, we can now understand why we use this getIDX inside the kernel, and we are calling the kernel with three buffers. 2 of them are A and B, and the last one is the resulting buffer. And workdiv, which is the work division we defined, and this is the kernel object instance, and this is the way to execute a kernel And
I have a question.
yes,
If the length of the array is longer than the number of threads, how does it work?
yeah, then we need to extend the work division to cover all the data. But therefore, work division should be selected depending on the data size. What would like to
Okay,
say?
so this code only works if the number of elements in the array is lower than the number of.
No, I mean, if we can change the work division using the okay, we can determine the work division using a function called let me show you getValidWorkDiv, which actually takes the whole grid size, which we usually use data size as the grid size. Therefore, work division is automatically generated for any backend. Therefore, in parallel programming, actually, we usually select the grid size equal to data size. But it shouldn't be like this. I mean, depending on your kernel, you can find different ways to process the whole data.
So again, just to clarify, it is absolutely not necessary.
Yeah.
The sizes, the number of threads you have versus the size of your array can be completely different. Your array can be huge, and it often is. The thing is, the way you map your vector to your actual physical computing course is totally up to you. Alpaka has some helpers which help you fit it, but you can also completely describe it on your own. And this is what we call the work division. And we will get to this eventually. We are not starting with this, but we will show this how you can distribute work among threads. Obviously, when a situation like this happens where you have a large vector and you have to fit it in a smaller number of threads, threads have to deal with multiple elements of the vector. And the way you can do this, you can do this in many ways. So
Yeah.
Get IDX is actually not returning. I mean, it's not returning a thread index, it's returning the index of an element to process.
No, it is indexing, it is returning thread index. But for now, we are using thread index as the data to access the data. But it shouldn't be like this. I mean, we can use thread index and data index could be different. But I mean, in order to make a thread use a portion of the data domain, we need to somehow create a mapping between the thread index and the data index. Therefore, your question is really important, but it shouldn't have to be one-to-one.
yeah. Yes. But your observation is absolutely correct.
Yeah.
Get index is actually giving you the index of the thread and not of the actual data element. And the example we are showing is somehow limited in this sense because you're absolutely right. You cannot add if they're too large.
Yeah, just one.
Now, I would like to talk about setting work division for different backends. I mean, because in GPUs, a block can have many threads, but in CPUs, each block can have one thread, or in other words, we have limited number of threads, and therefore, how work division is selected for different backends. That is important. For example, we have a single thread accelerator on the right and we have a multi-thread accelerator on the left. We can, should we change the work division if we change the backend? Or for example, we have a code which is running on CPUs And should we change the work division when we switch the backend to the GPU? Actually, this is the problem. For example, getting the thread index would work for different backends, but what will be the work division for calling the kernel? And there's an alpaka function which is actually called getValidWorkDiv, and it takes the kernel and the device and the kernel arguments, and kernel arguments kernel arguments are used for. It doesn't take kernel. It is an actually kernel config instance, but I will explain it later. Yeah, this is actually a generic way of creating a work division, and yeah, it is producing a valid work division, but it shouldn't be. It is. We cannot say that it is the optimal work division. Yeah, I have explained alpaka function qualifiers. Do you have any other questions about this session? In this session, I mainly explained getting the indexes and extents in the kernel, and getting the proper work division using a getValidWorkDiv function. Now, in this hands-on, we are just going to get the indexes and maybe extents, then try to print them parallelly in the kernel.
Thank you, Mehmet.